and thank you for coming to my talk about quantum reinforcement learning. I'm Dr. Sabine Wölk. I'm from the DLR Institute of Quanten-Technology, and I want to talk a little bit about what we have already done on the topic of quantum reinforcement learning and what we plan in the future. So maybe as a short motivation, I think all of us know that machine learning is a very powerful tool and we can do a lot with it. However, there are different ways of how to do machine learning. So when we think about machine learning, most people think about neural networks. So that's when we have a lot of data and then we are looking at this data and try to find similarities. Reinforcement learning is a little bit a different way of learning. It's a more creative way of learning, where we more or less start with no data. We only start with some rules. So the most famous example of what you can do with reinforcement learning is surely the AlphaGo algorithm from 2017, which was the first program which can beat human players in the game Go. And the interesting thing here is that they didn't start it with data, with how good human players play, but they started only with the rules of the game. So they implemented in this reinforcement learning algorithm some model where the computer knows what moves are allowed and how you can recognize that someone has won. And then the algorithm started to play against itself. And at the beginning, it just randomly tried different things. And each time when it won, it got a reward. And then the algorithm started to do more often actions which lead to a reward. And in this way, the algorithm learned to beat human players in the game of Go. And here we can see some learning curve and how often the algorithm uses a certain move, which is some kind of a good move. And here we see at the beginning, so here are how long the algorithm already learned. At the beginning, the algorithm did not use this move because it just didn't try it. And once it tried it, it used it from time to time, and once when it learned, that's a good move, it took this move more and more often. So reinforcement learning is all about exploration, trying different things, and exploitation, that's using things where you already know that they are good. And you can use reinforcement learning not only for teaching algorithm how to play games, but you can also use it, for example, for developing quantum error correction codes or to simulate turbulent flows. But the problem is this exploring can take a lot of time. So, and only once you find good action, you can start to learn. So finding good moves take a lot of time, and that's where our hybrid quantum classical learning agent comes into play, because quantum computer can help us to find good moves faster. So this will then be the outline of my talk. First, I will talk a little bit more about classical reinforcement learning, about how it works in general. Then I want to introduce our hybrid quantum classical learning agent. Then I show you some results we already obtained. And then we will have at some future project, which we have together with the Quantum Computing Initiative of the DLR. So this is a very simple and basic idea how reinforcement learning works. So in reinforcement learning, we have an agent, like for example this robot. And we have some environment which describes our problem. And then the agent can perform different actions, like for example here, going up, down, left or right. And if the agent performs some actions, then the environment changes, like it changes here the position. And the agent gets some information back about the current situation, that's called the percept S, and whether it gets a reward or not. So here in this simple case, the agent gets a reward if it finds this research station here. And mathematically, we can describe the behavior of the agent with the policy. So the policy is more or less a probability distribution, which says if we are in situation S, then we perform the action A with a certain probability. And at the beginning, for example, here in this case, all the probabilities for going up, down, left, or right are equal. And once it learns, it increases the probability for the good moves. And the goal of the agent is to maximize its long-term expected reward. So for example, if the agent is here at the beginning, no matter if it goes up, down, left, or right, it will not get a reward. Only when it finds here, in this case, this research station. So maybe it cannot get immediately a reward, but maybe in the future. And therefore, we sum up here in this long-term expected reward all the rewards we will get in the future, but with some discount. Because if the reward is very close, then it's much better than if it's far away. So this discount rate is some number smaller than 1 with some exponent k. And classical reinforcement learning is all about how to do this exploration and how to update these learning rules in order to maximize this long-term expected reward. And what can we do with the help of a quantum computer? So now we go from the classical world to the quantum world. And here we again have action, percepts, and reward. But in this scenario, instead of exchanging classical information about actions and percepts, the agent and the environment exchange quantum states. So we encode the actions A in some orthonormal quantum states and also the percepts and the reward. And then the agent and the environment in the scenario, they send back and forth quantum states. And here we also not only look at one single exchange of action and percept, but we look at a whole sequence. Like for example here, the agent, this blue figure, is allowed to make 3 steps, and then we check whether it has found the reward or not, and then everything is reset again, it starts again at this position. So if we have a quantum state, we can not only do like action 1 or action 2, but we can also do superposition of actions. So we start with a superposition of all action sequences of 3 steps. And then we send this sequence of actions to the environment. And then the environment determines the corresponding percepts and rewards. So at the end, after one round of 3 steps, we have this big quantum states which are entangled. We have superposition, we have entanglement, everything is quantum, and now we can do, okay, let's do a measurement and ask what is the probability to find a reward. And then the answer is very simple. In this case, it's roughly 5%, and that's exactly if the same probability than if we would just randomly choose classically one sequence of actions. So entanglement and superposition alone does not help us to speed anything up. What we also need is interference. So what we have to do is like we have to oracleize everything, which is if we have like our, for example, a completely deterministic and episodic environment is possible. It's also possible for other environment. And if we have this, then we can use this unitary from the environment to create some oracle. And this oracle is very similar to the Grover search algorithm, the oracle. Here we get a phase. So if this action sequence leads to a reward, we get a phase of minus. And if we don't get a reward, we don't get a phase. And here it's very interesting. So if we use this original unitary, then we get information about the percepts and the rewards. If we oracleize everything, first of all, we put the reward qubit into the minus state. And then we get no information about the percept and the reward. However, in this case, we can do amplitude amplification and increase the probability that the action that we measure will be an action which leads to a reward. In this case, if we do it once, like it's over 30%. So we can use a quantum computer to increase the probability to find an action sequence which leads to a reward. However, if we do this, we don't get any information about the actual reward or the percepts. So there's something we win and something we lose. And that's why we call it a hybrid quantum classical learning agent. So what we need to do is like we have to interchange between rounds of the game or rounds of searching where we do it in a quantum mechanical way. So that's like here. So instead of playing a sequence of actions with the probability p, we create a superposition of all possible action sequences weighted with the different probabilities which we get from the classical policy. Then we turn the reward qubit into the minus state and play, for example, k rounds, which then leads to k rounds of amplitude amplification. And after this k rounds of amplitude amplification, we do a measurement, and then we get a single sequence of action, and we know, if we've done everything correct, that this sequence of actions has a higher probability to lead to a reward. And then we take the sequence of actions and turn the reward qubit into the zero state, so we play one more or less classical round. And in this classical round, we get information about the action sequence, the reward, and the persets. And from this classical information, we can learn, we can update the classical policy, and can then decide again, do we want to play again quantum mechanically, or do we want to play now classically? And in a recent paper, we have shown that for certain environments, we can get something which is close to like a quadratic speed up of the learning time. So the learning time we define like the time we need on average to get to like a probability to get a reward with a certain percentage, like, I don't know, 30% or something like that. And then we see that the average learning time, if we have this hybrid quantum classical learning agent, is smaller or equal than the square root of the classical learning time times the average number of rewards we need in order to learn. And here there's like a prefactor. The prefactor depends on the on some theoretical on how to oracleize everything. It's more or less like a constant, like for example pi over 4. And with this, we can now compare, so we have like a classical agent. And this classical agent, it has some rules about how to explore the environment, how to update its policy and everything. And we know, like, if we have like a learning agent, if you compare to learning agent, there are always situations where one agent is better than the other and the other way around, depending on how you define the goal. And here in this example, we also have like two classical learning agents. So that's the learning curve of the solid learning curves. So in orange, we have a classical learning agent, which does a lot of only a little bit of exploration and a lot of exploitation. So if it finds a reward, it very likely uses the same things again. And here we see this one, it learns very fast. However, the average reward in this case, so in this case, we cannot only get a reward or no reward, but we can like rewards of different size between 1 and 32. And we see on average, the reward this agent finds is not that high, because it jumps directly to something it had already learned and then stops exploring. And if we turn this classical agent into a hybrid quantum agent, then we get as a learning curve this dashed line. And we see here this dashed line, this agent learns faster, but at the end, the solution is as good as for the classical agent. And the same thing happens for here this blue agent. So again, the solid line is some classical learning agent. It's a learning agent which explores more, therefore it learns slower, but the solution at the end is better. And again, here we have a hybrid quantum classical learning agent, the dashed line. And here we see it learns faster without sacrificing the quality of the solution. And so this was like the theory, and we've also performed some proof of principle experiment together with the group of Philip Walter from Vienna University. So here we use more or less a nanophotonic processor as a quantum computer. And we had like a very simple example with like 2 qubits. So we said, okay, it's like a toy example. We have like 1 qubit. And this 1 qubit can symbolize with the state 0 all the action sequences which don't lead to a reward, and the state 1 symbolizes all the action sequence which leads to a reward. And initially, the probability to find a reward was 1%. And we had a second qubit, which then represents our reward qubit. So this is like a schematic scheme of the quantum circuit. So depending on where we input like a photon into this photonic circuit, we get like different quantum states. And here we have like the classical circuit and the quantum circuit. And if you see like the different areas of the chip belong to the environment and the agent, and we see the environment does in the classical case and in the quantum case exactly the same thing. The only thing which we change is the behavior of the agent. So one time the agent behaves classically, and in the other time the agent behaves quantum mechanically. And what we do is we always run like one quantum circuit. And in this one quantum circuit, the probability to find a good sequence of action was increased. So we did a measurement, get as an action either 0 or 1. Then we played classically these actions, and if we got a reward, we updated the policy. And these are the experimental results. So first of all, we see that if we have like a pure classical agent and this hybrid agent, the average reward we get in the different rounds looks differently. So if we have like a classical agent can get a reward in each round. However, the probability to get a reward is very small. With the quantum agent, if we play a quantum round, we don't get information about a reward. It's like 0 reward. But if we play then the classical round with this information, then we get with higher probability a reward. So the blue ones are our hybrid agent, the average reward of our hybrid agent, and the red one is the average reward of our classical agent. So we need a way to make a fair comparison, because if we say, okay, who gets the most reward in every odd round, then the classical agent wins, and who gets most reward in every even round, in this case, the quantum agent wins. So we think a fair way is to distribute the reward the quantum agent gets between all the rounds it needs to get some information about the rewards. And that's what we call here the distributed case. So we split it up here in this case because we played every second round classically, all the reward of the quantum agent of these 2 rounds. Then we can see here at the learning curves, so here in orange, that's the learning curve of the classical agent. And here in green, we see the learning curve of our quantum agent. And here again, we see that the hybrid agent, it learns faster, and at the end, the solution is the same. And now you might ask, what is happening here? What's happening there? Well, the thing is, our hybrid agent can only get a reward in every second round. So in general, there's no way if we play like always one quantum round, one classical round to get a reward higher than 50%. So if we have like already learned quite a lot, then it's better to switch from playing one round quantum, one classical, to always play classical. And actually, this switching, it's not the best way to switch at 50%, but already a little bit earlier. And that's exactly what's happening here. So here we switch at around a probability of roughly 40%. And now we can ask, okay, what kind of speed up did we win? And so we defined the learning time as the time how long we needed to go up to 30%. And here you have to be careful, because here we only have like even epochs. So here at this point we have 100 even epochs. And we see roughly around here we have learned in the quantum case, and that's also the learning time for the quantum case we have measured. It's around 100 epochs, whereas the classical learning age needed in this case 266 epochs to learn. So even in this very simple case where we could only play like one quantum round and not several quantum rounds in a row, we already get some improvement. And the question is now, okay, this was like a toy example. This was a real example. We only said, okay, we had like only like a single qubit representing the action, and we only said, okay, we don't know what is the problem. We only know, okay, the probability to find a reward is like 1%. So what we are now investigating at the moment is like how to apply this learning agent to like real problems. So maybe as a short summary, so what we have learned, so we can get a quantum advantage if we let the agent and the environment play in a quantum mechanical way. So they interact by sending quantum states back and forth. And most of the time, we're not allowed to observe it. That's the quantum case. And because we only observe, like, after k rounds of playing quantum, we observe what's happening, we get like 1 over k less information. Because in the classical case, we can observe everything, we get information in every round. So even we get less information, the information is more valuable. Because in the classical case, we most of the time get information how to don't get a reward. Whereas in the quantum case, the probability to get information about how to get a reward is much higher, and therefore we can usually learn faster. And so this is now our outlook. So what we are doing, so we have like one project which is called Q-Learning. Here we look, for example, at how to apply this learning agent to different DLR applications. And the second thing we are investigating is how to implement or how to best implement such a quantum algorithm on real quantum hardware. Because real quantum hardware, we know, is limited in size, it has errors. So we have, if we want to have the best learning agent, we have to take this into account. And the other thing which we also have to take into account is, like, if we apply our problem to, like, our learning agent to a real problem, there are different problems might appear. Like, for example, in this maze problem, we usually don't know how many steps the agent needs in order to find the site. But if we have a quantum agent, we can also not observe. Like classically, we can say, okay, walk around until you find the site. But in the quantum case, we cannot do this. So we have to take this into account if we want to solve a real problem. And here we have like 4 examples. So here we say, okay, this is an example where we don't know the length, so we just set some lengths, and then the agent explores. And if we don't find the agent, if we don't find a reward, then we might increase the length. And here we see in blue the average number of rounds an agent, here in light blue a classical agent, needs if it always goes like 5, 6, or 7 steps. And in dark blue we see our hybrid agent. And here we see that there is like one optimal length. If we do like less steps or more steps, then the agent learns much slower. But we also see that it's true for the classical and the hybrid case, and nevertheless, even if you don't choose the optimal length in this example, the hybrid agent is still better. I mean, how this graph looks exactly, it will depend on the problem. So yes, there are problems where you can create in such a way that the classical agent also wins. And here in this project, we're also still searching for postdocs which are working with us on this problem. And then we also have like a different project. It's called QC Mobility. It's also a project of the Quantum Computing Initiative of the DLR. It's together with other DLR institutes which are working, for example, on air traffic, road traffic, rail, marine, and intermodal traffic. And here we are in general interested in quantum algorithms which can help to solve problems for these different traffic areas. So here we do like development of quantum algorithm in the hardware-software co-design. We want to then also let this algorithm which we developed here, it's not only quantum reinforcement learning, but also optimization and other things. We will then let them run on quantum hardware, which then belongs to the QCI in Ulm or Hamburg. And here there will be also calls for bits for industrial partners. So we are searching industrial partners from air, rail, traffic, and intermodal case. And we are also hiring here. So thank you for your attention. And are there any questions? Yes?
Es gibt ein Mikrofon.
Okay. Have you so far only simulated these systems which you've just presented, or have you actually run them on small quantum computers?
So actually, the first graph with these two agents, it was like a simulation. But the results from the photon experiment, this was like a real quantum computer.
Okay, so you've done both, but
yes.
Before you can move into real applications, you need better quantum computers.
There are two things, yes. First of all, we need like good quantum computers to solve real problems. And the other thing is also like, if you have like also the algorithm has to be adapted to the problem. So you have to work on both on the hardware, but also on the software. Yes?
Probably a naive question, just in the algorithm that you showed, you were using unitaries to perform the gates and to perform the whole algorithm. Do you think that instead using the noise in current devices, so using a Lindblad master equation to perform the algorithm itself would give some advantage? So you can harness the noise in the devices.
I mean, first of all, yes. If we do, I mean, we have to take the noise into account. It depends on the noise. I mean, if we have a lot of noise, then at the end everything will be classical and there will be no advantage. But it might be, I mean, maybe not in this case, but the question is also how does the agent decides what action to do. And this is something where noise might be also a good thing if you can create the noise in the correct way. Yes.
Thanks.